The universe speaks in whispers and roars. Sometimes it sends us postcard from the void, fragments of ice and stone that have traveled distances our minds can barely comprehend. In the autumn of 2024, one such messenger arrived at our cosmic doorstep, bearing secrets from beyond the familiar boundaries of our solar system. Its name, stamped with the bureaucratic precision of astronomical nomenclature, was 3I/Atlas. But what a mundane label for something so extraordinary. Imagine, if you will, standing on a beach at dawn. The waves roll in, each one a traveler from distant waters, carrying salt from far shores, stories written in foam. Now expand that beach to infinity. Expand those waves to include not water, but time itself, space itself, the very fabric of existence. This is where 3I/Atlas comes from. Not from our neighborhood, not from our solar family, but from somewhere else entirely. Somewhere other. It is the third interstellar object we have confirmed visiting our solar system, hence the 3I in its designation. The first was Oumuamua, that strange cigar-shaped enigma that sparked 1,000 theories and twice as many debates. Was it a comet? An asteroid? An alien spacecraft? The questions multiplied like stars in the night sky. Then came 2I/Borisov, a more conventional comet, reassuring in its familiarity even as it reminded us that we live in a neighborhood with open doors where visitors from distant realms can drop by unannounced. And now 3I/Atlas has joined this exclusive club of interstellar travelers. The Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, discovered it as it has discovered so many celestial objects that might someday pose a threat to our fragile blue marble. But 3I/Atlas poses no threat. It is merely passing through, a tourist in our cosmic city, here for a brief visit before continuing its eternal journey through the galaxy. How long has it been traveling? Millions of years? Billions? Time stretches differently in the depths of space, where there are no clocks, no calendars, only the slow dance of gravity and motion. What makes an object interstellar? The answer lies in its velocity, its trajectory, its relationship with the sun. Objects born in our solar system are bound to our star, tethered by invisible threads of gravity, following elliptical paths that bring them around again and again in predictable patterns. But interstellar objects? They move differently. They are unbound, free. Their velocities exceed the sun's escape velocity, meaning they have enough speed to break free from our star's gravitational embrace entirely. Picture a stone tied to a string whirling around your hand. As long as you hold the string, the stone circles endlessly. But cut that string, and suddenly the stone flies off in a straight line, free from its circular prison. This is what interstellar objects do. They have cut their strings long ago, perhaps in some stellar system light years away, and now they soar through the galaxy on trajectories that will never repeat, never circle back. The discovery of 3I/Atlas sent ripples through the astronomical community. Another one, the trickle of interstellar visitors was becoming less of a trickle and more of stream. Each discovery refined our understanding, sharpened our tools, expanded our perspective. We are learning to see what was always there, but remained invisible to us, hidden not by physical barriers, but by the limitations of our technology and attention. How many interstellar objects pass through our solar system each year? The estimates vary wildly, but some scientists believe that at any given moment, There might be several such wanderers within the orbit of Neptune. Most are too small, too dark, too distant to detect. They slip through our cosmic neighborhood like shy guests at a party, arriving and leaving without anyone noticing. But as our telescopes grow more powerful, as our surveys become more comprehensive, we catch more of them in our nets of light and data. 3I/Atlas likely originated in another star system entirely. Perhaps it formed around a star similar to our Sun, in a protoplanetary disk where ice and rock collided and merged in the cold outer reaches of that distant system. Perhaps it was a comet there, just as comets orbit in the frozen depths of our Oort cloud, waiting patiently for some gravitational nudge to send them spiraling inward. But something happened. Something changed. Maybe a star passed too close, its gravity reaching across the light years to disturb the delicate balance of that far-off system. Maybe a rogue planet, itself ejected from its home, crashed through like a bull in a china shop, scattering smaller bodies in all directions. Or perhaps it was something more subtle, the slow, patient work of countless small perturbations accumulating over eons until finally 3I/Atlas found itself on a trajectory that would carry it away from its birth star forever. Can you imagine that moment of departure? If 3I/Atlas could feel, what would it have felt as it crossed the threshold, as the gravity of its home star loosened its grip and released it into the interstellar medium? Would there be exhilaration, fear, or simply the cold, indifferent momentum of physics carrying it forward because there is nowhere else to go but forward? For millions of years, perhaps hundreds of millions, 3I/Atlas traveled through the space between stars. This journey is almost impossible to comprehend. Space, despite what science fiction often shows us, is almost perfectly empty. The distances are so vast, the volume so enormous, that even a galaxy containing hundreds of billions of stars is mostly void, mostly nothing. Between the stars, there is darkness. Not the romantic darkness of a moonless night on Earth, where starlight still filters through, where the atmosphere still holds warmth and the sounds of life. No, this is absolute darkness, perfect darkness, the kind that exists in the absence of any nearby source of light. The nearest stars would appear as distant points, no brighter than they appear to us from Earth. There would be no sun to warm 3I/Atlas, no planetary companions, no reference points to mark the passage of time or distance. Just the endless fall through emptiness. And yet, even that emptiness is not truly empty. The interstellar medium contains thin wisps of gas and dust, the debris of dead stars, and the raw material of stars yet to be born. 3I/Atlas would have drifted through these tenuous clouds. Each particle had encountered a tiny collision at cosmic speeds, slowly eroding its surface, sandblasting it with atoms over the millennia. The temperature in interstellar space hovers just a few degrees above absolute zero, that ultimate cold where even atoms barely move. Any ice on 3I/Atlas's surface would have frozen harder than steel, any organic compounds locked in a crystalline stasis. This is cold that goes beyond mere temperature. It is the cold of absence, the cold that comes from being far from any source of warmth, any source of energy, any source of life. But then, after a journey measured not in years or decades, but in geological epochs, 3I/Atlas encountered something new. A bubble of influence, a sphere of warmth and light, expanding outward from a middle-aged yellow star we call the Sun. The heliosphere, that vast region where the solar wind pushes back against the interstellar medium, must have been 3I/Atlas's first indication that its journey was about to change. As it fell inward, accelerating under the Sun's gravity, 3I/Atlas began to transform. The Sun's radiation, growing stronger with each passing day, began to warm its frozen surface. If 3I/Atlas contained volatile ices, water, carbon dioxide, methane, ammonia, these would begin to sublimate, turning directly from solid to gas without passing through a liquid phase. This is what makes a comet a comet. The development of a coma, that fuzzy cloud of gas and dust surrounding the nucleus, and potentially a tail pushed away from the Sun by radiation pressure and the solar wind. Did 3I/Atlas develop a tail? Did it blaze across our inner solar system like a banner unfurled, announcing its arrival? Or did it remain more subdued, its volatile content too low, or its trajectory too far from the Sun to put on a spectacular show? The observations would tell us, but the poetry of it, the sheer drama of an object from another star system entering ours and briefly becoming visible, briefly becoming something we could point our telescopes toward and study. That poetry remains regardless of the specific details. Astronomers around the world swung their instruments toward this visitor. Spectrographs analyzed the light reflecting from its surface and emitting from its coma, breaking that light into its component wavelengths to reveal the chemical fingerprints of the materials present. Telescopes measure its size, its rotation, its exact trajectory. Radio dishes listen for any signals, however unlikely. Every instrument we have developed to study the cosmos was brought to bear on this single object, this traveler from afar. What do they find? What secrets did 3I/Atlas reveal about its distant origin? The composition of interstellar objects offers a window into the formation conditions of other planetary systems. The ratio of different isotopes, the presence or absence of specific compounds, the physical structure of a nucleus. All of these details tell a story about the environment in which the object formed. Was its home system richer in heavy elements than ours? Did it form closer to or farther from its parent star? What was the temperature and density of the protoplanetary disk from which it condensed? These are not idle questions. By studying visitors from other star systems, we are essentially conducting a survey of planetary formation across the galaxy. Each interstellar object is a sample, a data point, a piece of the puzzle. And unlike distant exoplanets, which we can only study indirectly through their effects on their parent stars, interstellar objects pass close enough for detailed examination. We can see them, measure them, analyze them with a precision impossible for more distant objects. But beyond the science, beyond the data and the measurements and the academic papers, there is something more fundamental at work here. Something that touches on deeper questions about our place in the cosmos. We are not alone in our creation. This is what interstellar objects tell us. Not in the sense of finding alien life, though that would be exciting too, but in the sense that the processes that formed our solar system, that created Earth, that allowed life to emerge here, are not unique. They happen elsewhere. They happen around other stars. The universe is not a static museum with our solar system as the only exhibit, but a vibrant workshop where star systems form and evolve and sometimes cast off pieces of themselves into the greater void. 3I/Atlas formed around another star. It witnessed if inanimate objects can be said to witness anything, the early days of a planetary system not our own. It was there, however briefly, when worlds were being born light years away. And then it was expelled, sent on a journey that would ultimately bring it here, to our star, where beings on a small rocky planet would notice its passage and wonder about its origins. Is that not extraordinary? Is that not worth pausing to contemplate? We live in an era of casual miracles. We can communicate instantly with people on the opposite side of the planet. We carry in our pockets devices more powerful than the computers that sent humans to the moon. We have photographed the surface of Mars, sent probes to the outer planets, detected gravitational waves from colliding black holes billions of light years away. We have become so accustomed to wonder that we sometimes forget to wonder. But 3I/Atlas invites us to remember. It invites us to look up and realize that the universe is not a fixed stage, but a dynamic system, full of movement and change and interaction. It invites us to recognize that our solar system is not an island, but a port where visitors from other shores occasionally arrive. It invites us to expand our perspective beyond the comfortable boundaries of the familiar and recognize that we are part of something vastly larger than ourselves. The trajectory of 3I/Atlas will carry it past the sun and back out into interstellar space. It will not return. Its orbit is hyperbolic, unbound, meaning that our star's gravity will bend its path but not capture it. In a few years, it will cross back beyond the orbit of Neptune, beyond the scattered disk, beyond the Kuiper belt, and eventually back into the heliosphere's outer boundary. And then it will be gone, continuing its journey through the galaxy, perhaps toward another star system, perhaps toward nothing in particular. Where will it go? Will it drift for another million years before encountering another stellar system? Will it be captured by some future star's gravity, finding a new home in a new system billions of years from now? Or will it simply continue falling through the void forever, a solitary wanderer in an increasingly dark and empty universe as the galaxies spread apart and the stars burn out one by one? We cannot know. We can calculate its trajectory for a few centuries, perhaps a few millennia, but beyond that, the uncertainties compound. A slight gravitational tug from a passing star, an encounter with a molecular cloud, any number of events too small to predict or measure today could alter its path in unpredictable ways. 3I/Atlas's ultimate fate is written in probability, not certainty. But perhaps that is fitting. Perhaps the uncertainty is part of the message. Life itself is like this, is it not? We travel through time, much as 3I/Atlas travels through space. Moving forward because there is no other option, encountering obstacles and opportunities we cannot predict, occasionally passing close to others on their own journeys. We are shaped by our origins, by the circumstances of our formation, but we are not determined by them. We carry within us the material of our beginning, but what we become depends on the path we take and the encounters we have along the way. The discovery of interstellar objects has philosophical implications that extend beyond astronomy. It challenges our intuition about borders and boundaries. For most of human history, the known world was bounded by geography, by oceans and mountains and deserts that limited travel and trade and cultural exchange. Even as we developed better transportation, those boundaries remained meaningful. Different regions of Earth developed distinct cultures, distinct languages, distinct ways of understanding the world. But what boundaries exist in space? Where does one star system end and another begin? The answer, of course, is that such boundaries are arbitrary, conveniences for human categorization rather than fundamental features of reality. The sun's gravity extends infinitely far, growing weaker with distance, but never actually reaching zero. At some point, other stars' gravity becomes more significant, and we can say that we have left the sun's domain, but that transition is gradual, not sharp. This is why interstellar objects are so conceptually important. They demonstrate that the boundaries we imagine between star systems are permeable, porous, more like suggestion than walls. Matter flows between systems. Objects wander. The galaxy mixes itself over time, shuffling its contents like a cosmic card dealer preparing for the next hand. In a very real sense, we have already engaged in interstellar travel. Not us personally and not intentionally, but the atoms in our bodies, the elements that compose Earth itself. These came from interstellar space, from molecular clouds that collapsed to form our solar system. And before that, some of those atoms were forged in the cores of stars that lived and died long before our sun was born. We are, as Carl Sagan famously noted, made of star stuff. But we're also made of interstellar stuff, cloud stuff, the recycled material of the galaxy's long history. 3I/Atlas reminds us of this deep connection. It is not truly alien, not in the sense of being fundamentally different. It is made of the same elements, governed by the same physics, subject to the same laws that govern everything else in the universe. It is different only in its origin, in the specific star system where it formed. But that difference is enough to make it fascinating, enough to make it worthy of study, enough to make us pause and reflect on the nature of cosmic citizenship. What does it mean to be from Earth, when Earth itself is made of material that came from interstellar space? What does it mean to call our solar system home when interstellar objects pass through regularly, reminding us that we are part of a galactic community? These questions do not have simple answers, but they are worth asking. The increasing discovery rate of interstellar objects suggests that our understanding of the galaxy's dynamics is about to undergo a revolution similar to what happened when we started discovering exoplanets. Before 1992, we knew of no planets outside our solar system. Now we know of thousands, with more being discovered regularly. This flood of data has transformed our understanding of planetary formation, revealing a diversity of planetary systems far exceeding what we imagined based on our single example. Something similar may happen with interstellar objects. Each new discovery refines our models, challenges our assumptions, expands our data set. We're beginning to understand how common it is for objects to be ejected from their home systems, how they travel through the galaxy, what happens to them during their journeys, and what we can learn from studying them when they pass through our region of space. Some scientists have proposed missions to study interstellar objects up close. Imagine a spacecraft on standby, ready to launch at short notice when a new interstellar visitor is detected, racing to catch up with it before it leaves our solar system. Such a mission would be technically challenging. Interstellar objects move fast, and our current propulsion systems are slow by comparison, but not impossible. With sufficient warning and preparation, we could send a probe to rendezvous with one of these cosmic travelers, studying it up close, perhaps even landing on it, collecting samples, analyzing its composition in detail. What would we find? Would we discover organic compounds, the building blocks of life, suggesting that the chemistry necessary for biology is common throughout the galaxy? Would we find minerals and structures that indicate formation conditions very different from those in our solar system? Will we find anything completely unexpected, something that challenges our understanding of planetary formation or stellar evolution or galactic chemistry. The only way to know is to go and look. But even without such a mission, even with just the observations we can make from Earth and Earth orbit, 3I/Atlas offers valuable lessons. It teaches us humility, reminding us that our solar system is one of billions, not special except in the sense that it is ours. It teaches us curiosity, showing us that the universe is still full of mysteries, still capable of surprising us, still worthy of our attention and study. And it teaches us interconnectedness, demonstrating that the galaxy is a single, integrated system where matter and energy flow between regions, where what happens in one place can eventually affect another place light years away. Think about the journey of a single water molecule in 3I/Atlas's nucleus, assuming it contains water ice. That molecule formed perhaps 10 billion years ago in an interstellar cloud, condensing from vapor onto a dust grain in the cold vacuum. The cloud collapsed, forming a new star and protoplanetary disk. The molecule became part of a growing planetesimal in the outer regions of that system. For millions of years, it remained frozen, locked in place, part of a larger body orbiting a distant sun. Then came the ejection, perhaps violently, perhaps gradually, but eventually our water molecule found itself part of an object no longer bound to its home star, falling outward into interstellar space. For millions of years more, it traveled through the void, frozen to temperatures barely above absolute zero, experiencing nothing, changing nothing, simply existing in stasis as the light years slowly accumulated. And then our solar system, the gradual warming, the sun's radiation beginning to sublimate the ice. Perhaps our water molecule was released during 3I/Atlas's passage through our inner solar system, becoming part of the coma, ionized by solar ultraviolet radiation, pushed away by the solar wind. It might drift through our solar system now, a single molecule from another star, indistinguishable from the countless other water molecules, but carrying a history that spans light years and eons. Will that molecule eventually fall onto a planet? Might it, by some infinitesimal chance, end up on Earth, joining the water cycle, falling as rain, flowing in a river, being absorbed by a plant, consumed by an animal? Might you, reader, someday drink water that contains atoms from 3I/Atlas, linking you directly to another star system? The probability is vanishingly small, but it is not zero, and that alone is remarkable. This is the poetry of astronomy, the recognition that we are not separate from the cosmos, but part of it, that the artificial boundaries we draw are permeable, that everything is connected in ways both obvious and subtle. 3I/Atlas is a messenger, but not in the sense of carrying a deliberate message. Rather, it is a reminder, a symbol, a physical manifestation of the galaxy's essential unity. The study of interstellar objects also has practical implications. Understanding how common they are, what trajectories they follow, what they're made of, this knowledge could be crucial for humanity's long-term survival. Some interstellar objects might pose collision risks. While the chances of a dangerous impact are incredibly small, they are not zero, and knowing more about the population of interstellar visitors helps us assess and prepare for potential hazards. More optimistically, interstellar objects might represent resources. As humanity considers expanding beyond Earth, as we think about establishing permanent settlements in space or on other worlds, we need raw materials. water for drinking and agriculture, metals for construction, organic compounds for manufacturing. Interstellar objects contain these materials, and while catching one would be technically difficult, it is not impossible. Some futurists have proposed missions to intercept interstellar objects, mining them for resources rather than allowing them to simply pass through our system unused. There is something both ambitious and humble about such proposals. Ambitious in the audacity of catching objects moving at cosmic velocities for practical use. Humble in the recognition that we need not limit ourselves to resources found only in our immediate neighborhood, that we can think of the galaxy itself as our extended community, its wandering objects as potential assets rather than mere curiosities. But let us return from these practical considerations to the more philosophical. What does 3I/Atlas tell us about meaning, about purpose, about the narrative arc of existence? Objects like 3I/Atlas exist in a liminal space between order and chaos, between being part of something larger and being entirely alone. It was once part of a star system, bound by gravity, orbiting predictably one component in a larger structure. Then it was freed or exiled, depending on your perspective, sent wandering without destination or plan. Now it passes through our system, briefly interacting with us before continuing onward to, what? More wandering? Another brief interaction billions of years hence? Eventual destruction in some stellar collision or accretion onto a black hole. We project meaning onto such objects because that is what humans do. We cannot help but see narratives, metaphors, lessons in everything we observe. 3I/Atlas becomes a wanderer, a refugee, a messenger, an explorer. All human concepts apply to an inanimate lump of ice and rock. But perhaps this projection is not entirely misguided. Perhaps in seeing ourselves in 3I/Atlas, we are recognizing a genuine parallel, acknowledging that our own existence shares some fundamental characteristics with this cosmic wanderer. We too are products of specific formation conditions, the particular combination of genetics and environment that made us who we are. We too travel through time, unable to reverse course, carrying our origins with us but not determined by them. We too occasionally encounter others on their own journeys, interactions that change us in small or large ways before we continue on our separate paths. We too exist in a universe we did not choose, following trajectories shaped by forces beyond our control, trying to find meaning and purpose in circumstances that are fundamentally indifferent to our preferences. Is this a depressing realization? It could be. The cosmic perspective can make us feel small, insignificant, ephemeral. What does one human life matter when the universe is so vast, when objects like 3I/Atlas travel for millions of years between stars, when galaxies collide and merge in slow-motion ballets lasting billions of years? But could also be liberating. If the universe assigns no intrinsic meaning or purpose to anything, then we are free to create our own meaning, our own purpose. We are not cosmic mistakes or irrelevant accidents. Or rather, we are, but so is everything else, which means the playing field is level. The meaning in your life is just as real, just as valid, as the meaning in anything else in the universe, because all meaning is constructed by conscious beings trying to make sense of their experience. 3I/Atlas does not care that we observe it, study it, write about it. It continues on its trajectory regardless of our interest or ignorance. But we care, and that caring matters. It matters because we decide it matters, because we find value in understanding our cosmic context, in expanding our knowledge, in connecting with the larger universe of which we are part. The detection of interstellar objects is only possible because we built telescopes, developed mathematical tools to calculate orbits, created networks of observers who share data and collaborate across borders. None of this was inevitable. It required conscious choice, sustained effort, resources allocated to projects with no immediate practical payoff. We chose to look at the sky systematically, to track every moving object we could find, to analyze trajectories and compositions and physical properties. Why? Because we are curious. Because we want to know. Because understanding our place in the universe feels important, even if we cannot always articulate exactly why. This is one of the most distinctly human characteristics, the desire to know things that have no obvious survival value. A lion does not wonder about interstellar objects. A tree does not care where it came from beyond the immediate biological processes that sustain it. But humans? We want to know everything. We want to understand how things work, where they came from, where they're going, what all means. 3. Atlas benefits from this curiosity. It is studied, analyzed, discussed, written about. It becomes part of our collective knowledge, our shared understanding of the cosmos. In some small way, its existence is acknowledged, its journey documented, its passage through our system noted for posterity. Is there something poignant about this? An object that traveled millions of years in isolation, unobserved and unnoticed, finally encountering a place where beings capable of awareness mark its passage. It does not know we exist, cannot appreciate our attention, will not remember our observations. But we know it existed. We saw it. We recorded its properties and calculated its trajectory. We told its story, or at least the fragment of its story that intersects with ours. Humans have always told stories about the sky. Our ancestors looked up and saw patterns in the stars, inventing myths and legends to explain what they saw. They tracked the movements of planets, recorded eclipses, noted comets and meteors, interpreting these celestial events as omens, messages from the gods, signs of things to come. We no longer interpret astronomical phenomena as divine messages, but we still tell stories about them. We still find meaning in celestial events, though now that meaning is filtered through science rather than mythology. The discovery of 3I/Atlas is not an omen in the ancient sense, but it is significant. It tells us something about the universe and our place in it, something true and important, even if that truth is more subtle than the gods are angry or fortune will smile upon us. The story of 3I/Atlas is a story about connections across vast distances, about the permeability of boundaries, about being part of something larger than ourselves. It is a story about journeys without destinations, about transformation through experience, about carrying our origins with us while remaining open to new encounters. It is, in short, a very human story, even though the object at its center is about as inhuman as anything can be. As I write this, 3I/Atlas is somewhere in our solar system, following its calculated trajectory, indifferent to our attention. Photons from the sun strike its surface, warming it slightly, perhaps releasing small puffs of gas as ices sublimate. These gases expand into the vacuum, creating a thin coma visible to our telescopes. The object rotates. We have measured its rotation period, tumbling slowly as it travels, a motion perhaps imparted billions of years ago by some long-forgotten collision. In a few years, it will be gone, having completed its brief passage through our region of space. The observations will end. The telescopes will turn to other targets. Papers will be published, data archived, theories updated. And 3I/Atlas will fade back into the realm of the unobserved, traveling onward through the galaxy, its brief moment of celebrity over. But the knowledge remains. What we learn from 3I/Atlas becomes part of humanity's collective understanding, joining the vast library of information we have accumulated about the cosmos. Future students might read about it in textbooks, might see it referenced in papers about interstellar object populations, might use it as one data point among many in calculations about galactic dynamics. This is how science works. Not through single revolutionary discoveries, though those happen occasionally, but through the steady accumulation of data, the gradual refinement of models, the persistent questioning and testing and measuring that slowly builds a more accurate picture of reality. Each observation adds a small piece to the puzzle. Each object studied contributes to our understanding. And over time, these small contributions accumulate into something substantial, something meaningful, something that genuinely expands human knowledge. 3I/Atlas is one piece of that larger puzzle. It is not the most important piece. There are no most important pieces, really, just differently shaped pieces that fit in different places. But it is a piece nonetheless, and its contribution is real. Consider what we know now that we did not know before interstellar objects were discovered. We know that objects regularly escape from planetary systems and enter the interstellar medium. We know that these objects can travel vast distances and occasionally pass through other star systems. We know something about their compositions, their size distributions, their trajectories. We know that our solar system is not isolated, but exists in a dynamic galactic environment where exchange happens constantly. None of this is revolutionary in the sense of overturning fundamental physical theories, but all of it is important for understanding how the galaxy actually works, as opposed to how we theorized it might work. Before Oumuamua, we suspected that interstellar objects must exist. Planetary formation models predicted they should be ejected regularly, but we had never seen one. Now we have, multiple times, confirming our theories while also revealing unexpected details that require further investigation. This is the value of exploration, of looking systematically at the sky, of building better instruments, and conducting more thorough surveys. We find what we did not know we were looking for. We answer questions we did not know we had. We expand our understanding in ways that cannot be predicted in advance because, by definition, we do not know what we do not know. 3I/Atlas is a gift, in a sense. Not a gift given by anyone. The universe does not give gifts any more than it assigns meaning, but a gift nonetheless. It is an opportunity to learn, to measure, to understand something we could not access any other way. We cannot send probes to other star systems with current technology. They're simply too far away. But when pieces of other star systems come to us, we can study them, extracting information that would otherwise remain inaccessible. What will we do with this gift? The obvious answer is science. We will measure and analyze and publish papers. But beyond that, will the discovery of interstellar objects inspire the next generation of astronomers? Will it shape how we think about space exploration, about humanity's long-term future, about our place in the galaxy? Perhaps. Or perhaps 3I/Atlas will be remembered only as a footnote, one among many interstellar objects discovered in the early decades of the 21st century, notable only for being relatively early in the sequence. The long-term impact of any single discovery is hard to predict. What seems revolutionary at the time might fade into routine familiarity. What seems minor might, in retrospect, turn out to have been more significant than anyone realized. But impact and significance are not the only measures of value. There is also simple appreciation, the recognition that something interesting happened, that we learned something new, that the universe revealed a bit more of itself to our inquiring eyes. This appreciation does not require practical applications or revolutionary implications. It can exist for its own sake, a quiet satisfaction in knowledge gained, understanding deepened, curiosity satisfied. I wonder what the future holds for interstellar object studies. Will we develop better detection methods, catching smaller and more distant visitors? Will we launch that dedicated interception mission, sending a spacecraft to rendezvous with one of these cosmic wanderers? Will we eventually catalog enough interstellar objects to map their origins, tracing them back to specific stellar regions or even specific star systems? The possibilities are exciting, though many depend on technology and resources we do not yet have. But that has always been true of exploration. Columbus did not have GPS or satellite communication or modern navigation tools, but he sailed anyway. The Apollo astronauts worked with computers less powerful than a modern smartphone, but they reached the moon anyway. We work with what we have, pushing the boundaries of the possible, gradually expanding our capabilities until what was once impossible becomes routine. In a century or two, assuming humanity survives and continues developing technology, studying interstellar objects up close might be commonplace. We might have spacecraft constantly patrolling the outer solar system, ready to intercept and examine every visitor. We might have detailed catalogs of thousands of interstellar objects, enough to do real statistics, to identify trends and patterns, to understand not just individual objects but the entire population. Or we might not. The future is uncertain, and not all possibilities are positive. Climate change, war, economic collapse, pandemics. Any number of things could derail humanity's scientific progress. There is no guarantee that we will continue advancing, continue exploring, continue learning. The optimistic trajectory is not inevitable. But for now, in this moment, we are studying 3I/Atlas. We are learning what we can from this visitor. We are adding to human knowledge. We are participating in that grand project of understanding the universe, a project that has engaged curious humans for millennia and continues to engage us today. And that perhaps is enough. That is what we can do, what we are doing, what we will continue to do as long as we maintain our curiosity, our resources, our commitment to understanding. Each generation contributes what it can, building on what came before, laying foundations for what comes after. 3I/Atlas is our contribution, or part of it, a small piece of the vast puzzle, but a real piece nonetheless. The night sky continues to turn above us, indifferent to our attention, but not beyond our comprehension. The stars shine, the planets wander, and occasionally, if we look carefully enough, we spot something unusual, something that does not belong to our solar family, something from elsewhere, something other. 3I/Atlas is one such object. It came from somewhere beyond our sun's influence, traveled incomprehensible distances, passed through our system briefly, and will continue onward to destinations unknown. We saw it, we studied it, we told its story, and perhaps that is enough. Perhaps bearing witness, paying attention, acknowledging the existence of things beyond ourselves. Perhaps these acts have value in themselves, regardless of practical outcome or ultimate significance. Perhaps the simple fact of noticing, of caring enough to look carefully and think deeply, is what makes us human, what connects us to the larger universe, what gives meaning to our brief existence on this small planet orbiting an average star in a typical galaxy. 3I/Atlas does not need our acknowledgement, but we perhaps need to acknowledge it, need to recognize that we are part of something vast and ancient and ongoing, need to feel that connection to the cosmos that reminds us we are not alone, not isolated, not separate from the grand tapestry of existence. The universe is full of wonders. Most of them go unnoticed, unappreciated, unobserved. But some, a few, catch our attention, spark our curiosity, invite our study. 3I/Atlas is one of those few. And for that, we should be grateful. Not grateful to anyone in particular. Again, the universe does not distribute gifts, but grateful nonetheless. Grateful for the opportunity to learn, to discover. The mathematics of interstellar travel reveal truths that philosophy can only approximate. When astronomers calculated the hyperbolic excess velocity of 3I/Atlas, that crucial number indicating how fast it moves relative to the sun after accounting for gravitational acceleration, they were measuring freedom itself. Numbers on a screen, vectors plotted in three-dimensional space. These cold calculations tell a story of liberation that would make poets weep if they understood the language. Every object in our solar system moves within constraints. Comets swing around the sun in elongated ellipses, always returning, always bound. Asteroids circle in more regular paths, prisoners of equilibrium between inertia and gravity. Even the planets, massive as they are, follow predetermined tracks laid down billions of years ago when the solar nebula collapsed and sorted itself into concentric rings of debris. Everything has its place, its pattern, its predictable future, except the visitors. 3I/Atlas broke those rules not through defiance, but through circumstance. Somewhere in its past, the gravitational ledger was balanced differently. The calculations that govern orbital mechanics, those elegant equations that Newton gave us and Einstein refined, allow for solutions where binding energy becomes negative, where velocity exceeds escape threshold, where an object's future lies not in eternal return, but in perpetual departure. This is not poetry masquerading as science. This is science revealing poetry inherent in natural law. Think about what hyperbolic trajectory means in practical terms. As 3I/Atlas approached the sun, it accelerated, gaining speed as it fell into our star's gravitational well. This is normal. Everything does this. But the critical difference lies in what happens afterward. A bound object converts that kinetic energy back into potential energy as it climbs back out of the well, slowing down until it reaches its farthest point and begins falling inward again. The cycle repeats. Energy transforms but never escapes. But 3I/Atlas? It had too much speed from the start. Even after giving back all the energy it borrowed from the sun's gravity during its inward fall, it still possessed excess velocity, enough to keep climbing forever, to escape not just temporarily, but permanently. The sun's influence fades with distance, but never quickly enough to catch an object moving that fast. Where did that excess speed originate? From the gravitational assist of its ejection, from whatever planetary encounter or stellar passage flung it into interstellar space with enough momentum to overcome not just its home star's gravity, but every star it might encounter afterward. That initial kick, that first push into the void, set in motion a journey that may never end, that may continue until the universe itself grows cold and dark and the last stars gutter out in the incomprehensible distance of deep time. Can we trace it backward? Can we calculate where 3I/Atlas came from, identify the specific star system that birthed it? The answer is partially, imperfectly, probabilistically. Its current trajectory points back toward a general region of the galaxy. But trajectories degrade over time. The galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from the core, and 3I/Atlas has been traveling for so long that uncertainties multiply into impossibility. We can say it came from that direction, from somewhere in that quadrant of the sky, but pinpointing a specific system, that requires precision we do not possess, information we cannot extract from current data. This unknowing adds another layer to the mystery. 3I/Atlas is anonymous not just in name, but in origin, a foundling with no birth certificate, no family tree, no way to trace its lineage. We know it came from elsewhere, but elsewhere remains frustratingly vague. A direction rather than a destination, a vector pointing into the past rather than a map marking a specific location. Perhaps that anonymity is appropriate. Perhaps knowing exactly where it came from would somehow diminish it, would reduce the cosmic to the merely geographical. Better, maybe, to leave some mysteries unsolved, some questions unanswered, some blanks unfilled in the narrative. The composition of 3I/Atlas tells us more than its trajectory ever could. Spectroscopy, the analysis of light reflected from or emitted by an object, reveals chemical fingerprints with astonishing precision. Different elements and molecules absorb and emit light at specific wavelengths, creating patterns as unique as DNA, as identifiable as faces in a crowd. When light from the sun bounces off 3I/Atlas and travels to our telescopes, it carries information. Not information in the sense of conscious communication, but information in the thermodynamic sense. Organized data that reduces entropy, that tells us something we did not know before. The spectrum shows absorption lines where certain wavelengths are missing, emission lines where certain wavelengths are enhanced. From these patterns, we deduce composition. Does 3I/Atlas contain water ice? Almost certainly, if it shows cometary activity. Water is among the most common molecules in the universe, forming readily whenever hydrogen and oxygen meet in cold environments. Does it contain carbon dioxide, methane, ammonia? These are also common ices in cometary bodies, frozen volatiles that sublimate when warmed by sunlight, creating the coma and tail that make comets visible and beautiful. But the ratios matter. The relative abundances of different isotopes, the presence or absence of complex organic molecules, the mixture of refractory materials and volatile ices. These details paint a picture of formation conditions. Temperature, pressure, radiation environment, available elements, all of these factors influence what chemicals form and in what proportions. If 3I/Atlas's composition differs significantly from solar system comets, That difference tells us something about its birthplace. Perhaps it formed in a system richer in heavy elements. A later generation, star born from molecular clouds, already enriched by previous stellar generations. Perhaps it formed closer to or farther from its parent star than typical solar system comets. Perhaps the chemistry of its birth nebula was subtly different in ways that reflect local galactic variations. Every detail is a clue, every measurement a piece of evidence, every spectrum a testimony to conditions light years away and eons ago. The rotation of 3I/Atlas adds another dimension to our understanding. All solar system bodies rotate. This is a fundamental consequence of angular momentum conservation during formation. When a cloud of gas and dust collapses to form a star and planets, any initial rotation amplifies as the cloud shrinks, like an ice skater pulling in their arms to spin faster. The result is that stars rotate, planets rotate, moons rotate, asteroids and comets rotate. But the rotation rate and axis orientation depend on history. Collisions can speed up or slow down rotation, can tilt the axis, can even cause complex tumbling motions where the object wobbles chaotically rather than spinning smoothly around a fixed axis. By measuring 3I/Atlas's rotation period and light curve, the pattern of brightness variation as it spins, we can infer something about its shape, its surface properties, perhaps even its collision history. Does it rotate quickly, suggesting a violent past full of impacts? Or slowly, indicating a more quiescent history? Is its rotation axis aligned with its trajectory or tilted at some odd angle that hints at recent disturbance? These are questions observers attempt to answer, though the data is never perfect, never complete, always requiring interpretation and modeling to extract meaning from noise. The surface of 3I/Atlas, could we see it up close, would tell a more immediate story. Impact craters. Certainly, space is full of debris, and anything that has existed for millions or billions of years will have been struck many times. But the pattern and density of craters reveal age and history. Young surfaces show few craters. Old surfaces are saturated with them, overlapping circles and ellipses covering every available area. Are there jets, active regions where sublimating ice escapes preferentially, creating asymmetric forces that alter the object's trajectory? Many comets show such jets, visible as bright spots or streaks in high-resolution images. These jets can create measurable non-gravitational accelerations, tiny pushes that accumulate over time, slightly altering the object's path in ways pure gravitational calculations cannot predict. Has 3I/Atlas been weathered by cosmic rays during its long journey? Energetic particles permeate interstellar space, remnants of supernova explosions and other violent events. Over millions of years, these particles strike and penetrate surfaces, breaking chemical bonds, creating new compounds, darkening ices, and altering the optical properties of materials. The surface we see today may be substantially different from the pristine material that formed billions of years ago, modified by eons of radiation exposure. We cannot answer all these questions from Earth-based observations alone. We need closer looks, dedicated missions, perhaps eventually sample return. But even from afar, even with imperfect data and incomplete understanding, we learn. We piece together fragments of evidence into provisional narratives, stories that may need revision but represent our best current understanding of reality. The thermal properties of 3 3I/Atlas matter too? How much sunlight does it absorb? And how much does it reflect? This ratio, called albedo, tells us about surface composition and texture. Dark surfaces absorb more light, warm up more quickly, and may sublimate volatiles more efficiently. Bright surfaces reflect more light, stay cooler, and may preserve ices longer, even when exposed to solar radiation. Temperature determines which compounds sublimate at what distance from the sun. Water ice, for example, begins sublimating significantly when temperatures rise above roughly 180 Kelvin, which happens somewhere around Jupiter's orbit depending on exact conditions. Closer to the sun, carbon dioxide ice sublimates, then carbon monoxide, then other progressively more volatile compounds. By observing when and where 3I/Atlas develops its coma, how bright that coma becomes, what compounds are detected in it, we can map its thermal history during solar system passage. This is forensic astronomy, reconstructing events from traces and signatures, building timelines from fragmentary evidence, solving mysteries written in light and chemistry rather than words. The size of 3I/Atlas remains uncertain, as it does for most distant small bodies. We can measure brightness easily enough. That is just a matter of collecting photons with telescopes. But translating brightness into size requires knowing albedo, and albedo cannot be measured directly without thermal infrared observations or other specialized techniques. A small, bright object can appear identical to a large, dark object if they reflect the same total amount of light. This degeneracy frustrates attempts at precise size determination. We can estimate, we can bracket the possibilities within reasonable ranges, but we cannot say with certainty whether 3I/Atlas is 1 kilometer across or 10 without additional data. Size matters for multiple reasons. Larger objects have more mass, creating stronger gravitational fields that can hold onto volatiles more effectively. Larger objects have more internal heat, potentially from radioactive decay of long-lived isotopes, which might drive cryovolcanism or other geological activity. Larger objects are more likely to have retained primordial materials in their interiors, protected from radiation damage and thermal processing by outer layers of insulating material. But size also creates problems. Larger objects are more likely to have been heavily modified since formation, to have experienced differentiation where denser materials sink toward the center and lighter materials rise toward the surface. Smaller objects may be more pristine, more representative of original formation conditions, less altered by subsequent processes. There is no ideal size for a scientific target. Each scale reveals different information, answers different questions, provides different perspectives on the same underlying reality. The encounter geometry of 3I/Atlas's passage through our solar system determines what observations are possible. Did it pass close to Earth, allowing detailed study with smaller telescopes and shorter exposures? Or did it remain distant, requiring the largest instruments and longest integration times to gather sufficient signal? Did it pass through the ecliptic plane where most solar system bodies orbit? Or did it come from high galactic latitude, approaching from above or below the solar system's disk? The angle of approach affects visibility, affects which telescopes can observe it, affects how long it remains observable before departing. Timing matters too. Discovery early in the object's passage through the inner solar system allows for extensive observation campaigns, multiple instruments, coordinated efforts. Late discovery, when the object is already outbound, already fading, limits opportunities, forces rushed observations, leaves questions unanswered. This is the challenge of interstellar object astronomy. Unlike planets or asteroids or comets in bound orbits, which return predictably and can be studied at leisure over multiple apparitions, interstellar visitors pass through once and never return. We get one chance, one window of opportunity. Miss it, and the information is gone forever, inaccessible, lost to the vastness of space and time. This urgency adds pressure to observations, creates competition for telescope time, forces difficult decisions about resource allocation. Should major facilities dedicate nights to this target, delaying other scheduled projects? Should spacecraft missions be retargeted, sacrificing original objectives for the rare opportunity to study something truly unique? These are not easy questions, and different astronomers will answer them differently, depending on their priorities and perspectives. The scientific papers that emerge from 3I/Atlas observations will be technical, dense with jargon and mathematics, filled with tables and figures and error bars and statistical analyses. They will not read like the essay you are reading now. They will not wax poetic about cosmic journeys or philosophical implications. They will report measurements, describe methodologies, present results, discuss uncertainties, compare with models, and conclude with careful statements about what can and cannot be determined from available data. This is appropriate. Science has its own language, its own standards, its own ways of communicating that prioritize precision and reproducibility over accessibility and emotional resonance. The papers serve a specific purpose, advancing scientific knowledge through peer-reviewed publication, creating a permanent record that other researchers can build upon, contributing to the collective enterprise of understanding nature. But those papers, necessary as they are, do not exhaust the significance of 3I/Atlas. Numbers and measurements, spectra and orbital elements. These capture certain aspects of reality, but not others. They tell us what the object is made of, how fast it moves, where it came from, but they do not capture the existential vertigo of contemplating something that has traveled between stars, the wonder of recognizing that the galaxy is full of such wanderers, the quiet amazement at living in an era when we can detect and study these cosmic travelers. For that, we need different languages, the language of poetry and metaphor, of narrative and meaning, of philosophy and reflection. We need essays like this one, attempts to bridge the gap between technical understanding and human significance, efforts to translate data into something that resonates emotionally and intellectually beyond specialist communities. Both approaches are valid. Both are necessary. The scientific papers provide the foundation of knowledge, the reliable facts upon which everything else builds. The interpretive essays provide context and meaning, connecting those facts to larger frameworks of understanding, helping people see why they should care about measurements and orbital elements and spectroscopic data. Together, they form a more complete picture than either could alone. The legacy of 3I/Atlas will unfold over decades or longer. Some impacts will be immediate. The papers published within months of observation, the data added to catalogs and databases, the refinements to models of interstellar object populations. Other impacts will be delayed. Future missions inspired by this discovery, theoretical work building on these observations, technological developments driven by the desire to study similar objects better. And some impacts will be diffuse, impossible to trace to any single source. A student reads about 3I/Atlas and decides to study astronomy. A science fiction writer incorporates interstellar objects into their novel. A teacher uses the discovery to illustrate concepts in physics or mathematics. A child looks up at the night sky and wonders what else is out there, waiting to be discovered. These ripples spread through culture in ways that cannot be predicted or quantified, but are nonetheless real, nonetheless valuable, nonetheless part of the total impact of scientific discovery on human civilization. We are still in the early days of interstellar object astronomy. The field is young, the sample size small, the methodologies still being developed and refined. In many ways, we are like naturalists in the age of exploration, cataloging new species from distant lands, trying to understand patterns and relationships with limited data and imperfect tools. But we learn quickly. Each new discovery teaches us something, improves our detection methods, sharpens our theoretical models, expands our observational capabilities. The rate of discovery is increasing. What was once a shocking surprise, Oumuamua's detection sent waves through the astronomical community, is becoming more routine. Not mundane, not uninteresting, but expected. We now know that interstellar objects pass through regularly, and we're getting better at spotting them. This transition from surprise to expectation marks scientific maturity. Fields typically progress through stages. First, the shocking discovery that challenges existing understanding. Then, the scramble to explain and understand. Then, the systematic study and catalog. There exists within 3I/Atlas something no spacecraft has ever captured, no laboratory has ever synthesized, no archive has ever stored. A physical record of conditions that existed in another planetary system during its formation epoch. This is not metaphorical history. This is literal preservation. Molecular memory frozen at temperatures where chemical reactions effectively cease, where time itself seems to stop at the atomic level. Consider the nucleus, that solid core hidden beneath whatever coma develops during solar approach. Within that nucleus, layered like sedimentary rock or tree rings, lies material that accreted over time as the object grew from microscopic dust grains to a body kilometers across. The innermost layers formed first, perhaps when the parent star was still a protostar, still gathering mass from its surrounding disk, still brightening toward main sequence stability. The outermost layers formed later, after the disk had evolved, after chemical gradients had redistributed materials, after the first planets had begun sweeping their orbital zones clean. Each layer carries isotopic signatures, ratios of elements that depend on nuclear processes in previous stellar generations. Oxygen exists in 3 stable isotopes: oxygen 16, oxygen 17, oxygen 18. The ratios between these isotopes vary depending on where and when the material formed. Different regions of molecular clouds show different ratios. Different times in galactic history show different ratios. These variations are subtle, measured in parts per thousand, but they are detectable and they are meaningful. If we could drill into 3I/Atlas's core, extracting samples from different depths, we could read those isotopic variations like pages in a book. We could map how its parent system's chemistry evolved during the formation period. We could compare those ratios to solar system materials, identifying similarities and differences, piecing together whether its birth environment was richer or poorer in heavy elements, whether its molecular cloud had been enriched by recent supernovae or depleted by previous star formation. This is cosmochemistry, the study of chemical history written in atomic nuclei, preserved across billions of years, waiting for someone with the right tools to read it. But extraction requires proximity, requires landing, drilling, sampling, analysis. From Earth, even from orbit, we cannot access those deep layers. We can only study the surface, and surfaces lie. Surfaces are weathered, altered, contaminated by cosmic ray exposure and solar radiation and impacts, and all the other processes that modify material over geological timescales. Still, even surface composition tells us something. The presence of certain organic molecules, complex carbon compounds that form through photochemistry or radiation chemistry, indicates specific formation environments. Some organics require ultraviolet radiation, suggesting formation in regions exposed to stellar light. Others require shielding, forming only in dense, dark regions where starlight cannot penetrate. The mix of molecules, their relative abundances, their structural complexity, all of these details constrain formation scenarios. Amino acids, the building blocks of proteins, can form in interstellar environments through entirely non-biological processes. If 3I/Atlas contains amino acids, and many comets do, their chirality matters. Life on Earth uses almost exclusively left-handed amino acids, a symmetry breaking that remains mysterious. If interstellar objects show similar handedness preferences, that suggests abiotic processes can generate such asymmetries, weakening arguments that life is required to produce them. If they show different patterns, that raises new questions about why Earth's biochemistry chose the particular handedness it did. These are not idle speculations. Missions to comets have detected amino acids, have analyzed their structures, have found both left-handed and right-handed versions. The data exists. The questions are real. And interstellar objects add another dimension to these investigations by providing samples from different chemical environments, different formation conditions, different stellar neighborhoods. The mineralogy of 3I/Atlas's nucleus, the crystalline structures of solid materials, the mineral phases present, the grain sizes and morphologies, records thermal history. Some minerals form only at high temperatures, requiring heating events that melt or partially melt the material. Others form only in cold environments, never experiencing significant warmth. The crystal structures themselves preserve information. Larger crystals indicate slower cooling, more time for atomic rearrangement. Smaller crystals indicate rapid cooling, quenching that locked-in structure before growth could proceed. If 3I/Atlas contains high-temperature minerals, that indicates heating at some point in its history. Perhaps it formed closer to its parent star than we might assume. Perhaps it experienced a collision energetic enough to partially melt material. Perhaps radioactive decay of short-lived isotopes, aluminum, 26, iron, 60, generated enough internal heat to drive differentiation and melting in the early solar system. Or perhaps it contains only low-temperature minerals, suggesting perpetual cold, formation in the outer reaches of a planetary system, never disturbed by violent events, never heated beyond the initial warmth of accretion. Each scenario paints a different picture, tells a different story, implies different formation conditions. We infer these stories from indirect evidence, from spectra and colors and brightness variations, but the ambiguity frustrates. We want certainty. We want to hold a piece of 3I/Atlas in our hands, to analyze it with laboratory instruments that offer precision impossible for telescopes. We want what we cannot yet have: direct access to interstellar material while it still resides in identifiable interstellar objects rather than dispersed throughout the solar system as micrometeorites and dust. The dream persists of intercepting one of these visitors, matching velocity, landing, collecting samples, returning them to Earth. Technically possible, economically expensive, politically difficult to justify. Space missions compete for limited funding against countless other priorities: terrestrial and celestial, scientific and practical. Why spend billions to sample an interstellar object when that money could fund hospitals, schools, infrastructure, 1,000 more immediate concerns? The question is fair, even if it hurts to ask. Resources are finite. Choices have consequences. Every dollar spent on space exploration is a dollar not spent elsewhere. And those elsewhere options include genuine human needs, real suffering that money could alleviate. Yet the counterargument holds weight too. Understanding our cosmic context, knowing our place in the universe, recognizing that we are part of something vastly larger than terrestrial politics or economics. This has value that transcends immediate utility. Not everyone will find that argument compelling, and that is fine. Reasonable people can disagree about priorities without either being wrong. But for those who do find cosmic understanding valuable, who believe that knowledge has worth beyond practical application, who think that humanity's long-term future depends on becoming a spacefaring species, for those people, studying interstellar objects is not a luxury, but a necessity, an investment in understanding that will pay dividends measured not in years or decades, but in centuries and millennia. The velocity distribution of interstellar objects passing through the solar system follows patterns dictated by galactic dynamics. Stars orbit the galactic center at speeds that depend on their distance from the core. Inner stars orbit faster, outer stars slower, creating differential rotation that shears apart structures and mixes populations over time. This means objects ejected from different stellar systems arrive at our solar system with different velocities, different approach angles, different energies. By measuring these velocities and angles, by building statistical models of the interstellar object population, we can infer properties of the galaxy's small body population, how many such objects exist, how they are distributed spatially, how ejection mechanisms vary with stellar type and system architecture. Current estimates suggest trillions of interstellar objects larger than a few tens of meters exist in the Milky Way at any given time. Trillions. The number strains comprehension, but it follows logically from planetary formation models combined with ejection rates estimated from simulations and observations. Every star system produces far more planetesimals than it retains. The excess gets ejected, contributing to a vast galactic reservoir of unbound objects. Most are small, fragments, debris, chips knocked off larger bodies during collisions. But some are large as small planets, behemoths wandering the void with masses measured in Earth masses rather than kilograms. These superinterstellar objects remain hypothetical. We have not detected any because they are rare and hard to see. But models predict they should exist. Occasional giants cast out from their birth systems through gravitational interactions with massive planets. Imagine encountering one of those. Imagine a Mars-sized object passing through the outer solar system, its gravity perturbing orbits, its presence unmistakable even from billions of kilometers away. What could we learn from something that large? What histories could we read in its geology, its atmosphere if it retained one, its internal structure if we could probe it seismically. These are dreams for future generations, scenarios possible only with detection systems far more sensitive than anything currently operational. But technology improves. Telescopes grow larger and more sophisticated. Algorithms become more efficient at identifying unusual trajectories amid the noise of bound solar system objects. What seems impossible today becomes routine tomorrow, given sufficient time and effort. The philosophical implications of a galaxy full of wandering objects deserve deeper consideration. We tend to think of star systems as discrete entities, isolated islands in the void, each developing independently without influence from neighbors. This picture is not wrong, exactly, but it is incomplete. Star systems exchange material. Ejection sends objects into interstellar space. Accretion captures some fraction of passing interstellar objects. The exchange rate is tiny. Most systems will never capture anything significant, but over billions of years, even tiny rates accumulate. This means planetary systems are not entirely closed. They leak and occasionally absorb. Material mixes, not rapidly or efficiently, but genuinely. An atom formed in one system can end up in another through this process. Not many atoms, not a significant fraction, but some. Enough that if we could trace every atom in Earth back to its origin, some fraction, tiny but non-zero, would trace not to our solar nebula, but to material that originated elsewhere, that was ejected from another system, that wandered interstellar space before being captured by our forming solar system. Is there interstellar material in your body right now? Statistical probability suggests yes. A few atoms, perhaps a few thousand or million, but some. You are made partly of other star systems, quite literally, through this slow mixing process that operates on galactic timescales. Does knowing this change anything? Practically, no. A carbon atom is a carbon atom regardless of origin. But conceptually, symbolically, it reinforces that borders are artificial, that separation is illusion, that we are connected to the galaxy in ways both abstract and concrete. 3. Atlas participated in this mixing. It carried material from its birth system into ours. If it sheds dust, if small particles escape its nucleus and drift into the solar system, some of that material will eventually fall onto planets. Onto Earth, potentially. Onto you, eventually, through the same processes that cycle all matter through the biosphere over geological time. This is not mysticism. This is basic mass conservation and planetary science. Everything on Earth came from somewhere, from the solar nebula, from impactors from comets and asteroids and dust. Interstellar contributions are small, but they exist. 3I/Atlas's contribution is smaller still, effectively unmeasurable in any individual sample, but real nonetheless. The psychological impact of recognizing such connections varies between individuals. Some find it alienating. We are not even purely solar system material, but mongrels with ancestry stretching to unknown stars. Others find it comforting. We are part of a galactic community connected to the broader universe through tangible physical links, not separate but integrated. Neither reaction is more correct than the other. Both are valid responses to the same information, filtered through different value systems and emotional frameworks. The energy budget of ejecting 3I/Atlas from its parent system was enormous. Accelerating even a kilometer-sized object to velocities exceeding escape speed requires gravitational interactions with bodies far more massive, planets, likely. The mechanics work through what is called gravitational slingshot or gravitational assist. An object approaching a massive body gains speed if its trajectory is oriented correctly, extracting kinetic energy from the planet's orbital motion around the star. This process cannot create energy. Conservation laws remain inviolate, but it can transfer energy from one object to another. The planet loses an infinitesimal amount of orbital energy, slowing fractionally in its orbit. The small object gains that energy, accelerating dramatically. For typical planetary masses and small object masses, the planet's change is unmeasurably small. But the small object's change is huge, potentially sufficient to reach escape velocity. This implies 3I/Atlas had at least one close encounter with a planet in its birth system, possibly multiple encounters that progressively boosted its energy until finally it exceeded escape threshold. Each encounter was a dice roll. Most would result in energy loss or minimal gain, but occasionally the geometry aligns perfectly. The phase-space trajectory threads through exactly the right region, and acceleration occurs. Chance plays a role, but so does architecture. Systems with giant planets in eccentric orbits, where close encounters happen more frequently, eject more objects than systems with circular, well-spaced orbits. Systems with multiple giant planets scatter objects more efficiently than single-planet systems. The ejection rate depends on system configuration, and that configuration depends on formation history. By studying populations of interstellar objects, by measuring their velocity distributions and chemical compositions and size distributions, we are indirectly studying planetary system architectures throughout the galaxy. Each interstellar object is a sample not just of its parent body, but of the system that ejected it, carrying information about planetary masses, orbital configurations, dynamical histories. This is forensic galactic astronomy, inferring properties of unseen systems from traces they leave in the population of wanderers they produce. The radiation environment experienced by 3I/Atlas during its interstellar journey was hostile in ways difficult to appreciate without understanding particle physics. Cosmic rays, mostly protons, some heavier nuclei, stream through the galaxy at relativistic speeds, accelerated by supernova shocks and other violent astrophysical processes. These particles carry enormous energy, enough to penetrate deeply into solid material, enough to shatter atomic nuclei and create cascades of secondary particles. Over millions of years, cosmic ray bombardment modifies surfaces and near surfaces. Chemical bonds break, new compounds form, crystalline structures become amorphous. Isotopic ratios change as nuclear reactions create or destroy specific isotopes. The result is a processed rind, a radiation-damaged layer that differs compositionally and structurally from pristine interior material. Measuring this radiation-damaged layer provides chronological information. The depth of penetration, the degree of modification, the specific nuclear products created. These depend on exposure time. By modeling cosmic ray fluxes and interaction cross-sections, we can estimate how long material was exposed to interstellar radiation, providing a minimum age for the object's ejection from its parent system. This chronometry is imperfect. Cosmic ray fluxes vary spatially and temporally. Interaction cross-sections have uncertainties, Measurements are difficult from remote observations, but it is real. It provides constraints that would otherwise be unavailable, tying physics to history, connecting present observations to past events. The magnetic field of 3I/Atlas, if it possesses one, remains unmeasured and likely unmeasurable with current technology. Small bodies typically lack significant magnetic fields. They require either liquid metallic cores generating dynamo fields or remnant magnetization from formation in magnetized environments. Most asteroids and comets show no detectable fields, but if 3I/Atlas does possess residual magnetization, that would tell us something extraordinary about its formation environment. It would indicate that its parent system's protoplanetary disk was strongly magnetized during the epoch when 3I/Atlas formed, allowing magnetic minerals to align with the field and lock in that alignment as temperatures dropped below the Curie point. Such magnetization would be weak, microtesla or nanotesla levels, but potentially detectable with sensitive magnetometers on a flyby or orbiter mission. The field orientation would record the geometry of the original disk field, providing a snapshot of conditions billions of years ago in a system light years away. This is speculative technology, future capability rather than present reality. But speculation has value. It identifies what would be useful to measure, what questions we could answer with better tools, what discoveries await if we invest in developing those tools. The albedo variations across 3I/Atlas's surface, if it has any, would indicate compositional or textural heterogeneity. Comets often show such variations, with darker, dust-rich regions contrasting against brighter, ice-rich regions. The pattern tells us about activity history. Bright regions may be recently exposed by sublimation, removing overlying dust, while dark regions may be ancient surfaces heavily modified by radiation and micrometeorite impacts. Mapping these patterns requires resolved imaging, which requires proximity. From Earth, 3I/Atlas appears point-like, a dot of light without spatial structure. We can measure overall brightness and color, but not how those properties vary across the surface. That information remains locked behind distance and angular resolution limits. Yet even unresolved observations contain information. The light curve, brightness as a function of time, reflects both rotation and shape. An elongated object spinning end over end will appear brighter when presenting its broadside to Earth and dimmer when edge-on, creating periodic variations that reveal not the surface itself, but the geometry underlying it. The amplitude of these variations constrains axial ratios. Larger brightness changes indicate more extreme elongation. Smaller changes suggest a more spherical form. Some interstellar objects exhibit light curves suggesting shapes unlike anything common in our solar system. Oumuamua's extreme brightness variations implied an axial ratio of at least 10:1, perhaps higher. A needle or a pancake, geometries that strained conventional formation models. Whether 3I/Atlas shares such peculiarity or presents more conventional proportions depends on data still being analyzed, papers still being written, conclusions still being debated in conference halls and email exchanges between researchers. Shape affects much beyond mere appearance. Elongated objects experience different tidal stresses when passing close to stars or planets. They tumble differently, their rotation potentially chaotic rather than stable. They shed material asymmetrically if active, creating jets that torque the nucleus and alter trajectories in complex ways. Shape is not decoration, but dynamical player, influencing evolution and determining outcomes. The dust surrounding 3I/Atlas, if it develops a coma, consists of particles ranging from nanometers to millimeters in size. These particles scatter and absorb sunlight, making the coma visible, but they also carry momentum imparted by that sunlight. Radiation pressure, the physical push exerted by photons striking matter, accelerates small particles outward from the nucleus, creating the classic cometary tail that always points away from the sun regardless of the object's direction of motion. But particle size determines acceleration. Smaller particles, with higher surface area to mass ratios, accelerate faster and get pushed farther. Larger particles, with lower ratios, accelerate more slowly and remain closer to the nucleus. This size-dependent sorting creates spatial structure within the coma and tail, with particle size distributions varying with distance from the nucleus. By analyzing this structure, measuring how brightness and color vary spatially within the coma, we can infer the size distribution of ejected particles. That distribution, in turn, constrains fragmentation processes, how ice sublimate, how dust is released, how larger aggregates break apart into smaller pieces. Each mechanism leaves distinct signatures, patterns that trained observers can read like handwriting analysts identifying authorship. The gas-to-dust ratio in 3I/Atlas's coma, should it develop one, provides another diagnostic. Ice-rich objects produce more gas relative to dust. Dust-rich objects produce less gas. The ratio depends on composition, internal structure, thermal history, and recent activity patterns. Comets in our solar system show ratios varying by orders of magnitude, from gas-dominated to dust-dominated, reflecting the diversity of formation conditions and evolutionary paths. If 3I/Atlas's ratio differs systematically from solar system norms, that difference might indicate chemical variations in its parent disk, perhaps lower volatile content, or higher refractory content, or different temperature gradients during formation. Or it might indicate nothing about formation and everything about subsequent evolution. Preferential loss of volatiles during interstellar transit, surface modification that sealed off-gas escape routes, impact gardening that altered near-surface structure, disentangling formation signatures from evolutionary modifications is among the central challenges in planetary science. Every object we observe is a palimpsest, original text overwritten by subsequent events, with layers of history superimposed until reading any single chapter becomes an exercise in forensic reconstruction. The trajectory perturbations caused by outgassing, non-gravitational forces arising when sublimating gas pushes asymmetrically on the nucleus, are small but measurable for objects on bound orbits. These perturbations accumulate over multiple passes, making long-term prediction difficult without accounting for them. For interstellar objects, which pass through only once, the perturbations are less problematic for prediction, but more interesting for diagnosis. The magnitude of non-gravitational acceleration depends on activity level, nucleus size, rotation rate, and active area distribution. By measuring how much 3I/Atlas's trajectory deviates from a pure gravitational path, we can estimate these properties, adding another constraint to the growing pile of data that collectively characterizes the object. This is how science builds understanding, not through single definitive measurements, but through accumulation of complementary constraints, each measurement narrowing the range of possibilities each observation excluding certain scenarios while remaining consistent with others. Eventually, enough constraints accumulate that only one scenario remains plausible, or at least that some scenarios become overwhelmingly more probable than alternatives. The polarization of sunlight reflected from 3I/Atlas contains information invisible to standard photometry. Light can oscillate in any direction perpendicular to its propagation, but scattering from surfaces and dust particles preferentially selects certain polarization directions over others. The degree and orientation of this polarization depends on particle size, shape, composition, and viewing geometry. Measurements of polarization versus phase angle, the angle between sun, object, and observer, create diagnostic curves that differ for various materials and structures. By comparing 3I/Atlas's polarization behavior to laboratory measurements and theoretical models, we can further constrain surface and coma properties, adding yet another piece to the puzzle. These specialized observations require dedicated equipment and careful calibration. Not every telescope can measure polarization accurately. Not every observer has access to the necessary instruments. This creates observational biases where certain properties are well measured while others remain poorly constrained, not because the data doesn't exist in principle, but because collecting it requires resources not always available. The infrared signature of 3I/Atlas, emitted thermal radiation rather than reflected sunlight, provides temperature measurements unobtainable from visible light observations alone. Warmer regions emit more infrared radiation. Cooler regions emit less. By mapping infrared brightness across the surface, again, requiring proximity for spatial resolution, we could identify active regions, thermal anomalies, areas where sublimation cools the surface below average temperatures. Infrared spectroscopy accesses molecular vibrations and rotations, providing chemical identification complementary to visible light spectroscopy, which samples electronic transitions. Some molecules are best detected in infrared, others in visible or ultraviolet. Comprehensive characterization requires observations across the electromagnetic spectrum, from radio through visible to ultraviolet and beyond, each wavelength regime contributing unique information. But atmospheric absorption blocks many infrared wavelengths from reaching ground-based telescopes, requiring space-based observations or airborne platforms flying above most atmospheric water vapor. This adds cost and complexity, limiting how often and how thoroughly infrared observations can be conducted. The problem of incomplete information pervades observational astronomy. We always wish for more data, better data, different data. We make do with what we can get, extracting maximum insight from imperfect measurements, acknowledging uncertainties, recognizing limits, but proceeding nonetheless because partial knowledge exceeds total ignorance. The networks that coordinate observations of transient targets like 3I/Atlas span the globe, linking professional and amateur astronomers in collaborative efforts that would have been impossible decades ago. When something interesting is discovered, alerts propagate through these networks within minutes, mobilizing observers at institutions with relevant capabilities and available telescope time. This democratization of astronomy, where hobbyists with modest equipment contribute meaningful data to professional research programs, represents a cultural shift as significant as any technological advance. Science becomes more participatory, more distributed, more resilient to single points of failure. If one observatory is clouded out, another picks up the observation. If one telescope breaks, others continue coverage. The human dimension of astronomical research, the collaborations and competitions, the friendships and rivalries, the shared excitement of discovery, and the frustration of ambiguous results, rarely appears in published papers, but shapes outcomes nonetheless. Science is a social enterprise conducted by people with emotions and biases and personal histories that influence how they interpret data, what questions they ask, what answers they find plausible. Acknowledging this human element does not undermine scientific objectivity. If anything, it strengthens it by recognizing that objectivity is aspirational rather than automatic, something we must actively work toward rather than passively assume. By being aware of potential biases, we can design methods that minimize their impact, creating systems where personal preconceptions matter less than empirical evidence. The legacy data from 3I/Atlas will outlive everyone currently studying it. Observations archived in digital repositories, accessible to future researchers who will bring new questions and new analytical techniques, extracting insights impossible with current methods. This longevity transforms each observation from a single-use measurement into a permanent resource, a gift to the future that costs nothing to maintain once properly stored. Archival astronomy, mining old data for new discoveries, has become increasingly important as data volumes grow and analytical capabilities advance. Objects studied decades ago are revisited with modern algorithms, revealing details missed by earlier analyses. Surveys conducted for one purpose prove valuable for completely different purposes. Data originally collected to answer one question, finding new life addressing another. This means observing 3I/Atlas thoroughly now creates value, extending far beyond immediate scientific papers. We are building a resource that will serve researchers for generations, supporting investigations we cannot currently imagine, answering questions not yet formulated, contributing to understanding in ways impossible to predict. The cost-benefit calculation for scientific research must account for this long-term value. Measuring return on investment only in terms of immediate results undervalues research that builds foundations, creates resources, enables future work. Some investments pay off quickly. Others pay off slowly, but more substantially. Both types are necessary for healthy scientific progress. The naming of interstellar objects follows conventions established by the International Astronomical Union, the organization responsible for nomenclature across astronomy. The I designation indicates interstellar nature, distinguishing these objects from comets, C, and asteroids, A, in bound orbits. The number before the I indicates discovery order, first, second, third. The name after the I identifies the survey or observer who first detected it. These systematic names lack poetry, but provide unambiguous identification. Everyone knows exactly which object 3I/Atlas refers to, regardless of language or cultural background. This standardization facilitates communication in an increasingly international scientific community where researchers from dozens of countries collaborate on shared projects. Yet the system also strips away meaning, reducing objects with rich histories to bureaucratic labels. The tension between systematic clarity and evocative naming is not unique to astronomy. Taxonomists face similar challenges naming species, geographers naming geographic features, parents naming children. We want names that convey information while also resonating emotionally, labels that clarify while also inspiring. Perhaps both types of names can coexist, as they do for planets where systematic designations like HD 209458b coexist with unofficial nicknames like Osiris. The formal name ensures precision. The informal name provides connection. Both serve valid purposes. The final observations of 3I/Atlas will occur when it has faded beyond detection limits, too distant and dim for even the largest telescopes to track reliably. That moment, whenever it comes, will be anticlimactic. Not a dramatic exit, but a gradual fade-out, brightness dropping below signal-to-noise thresholds until distinguishing the object from background noise becomes impossible. There will be no farewell, no acknowledgement of departure. Observers will simply move on to other targets, other projects, other objects demanding attention. 3I/Atlas will continue outward, unobserved, returning to the anonymity from which it briefly emerged. This asymmetry between our perspective and the object's reality highlights the anthropocentric nature of astronomical observation. Events are significant or insignificant based on whether we can detect them, not based on any intrinsic property. 3I/Atlas's passage through our solar system is notable to us because we are here, because we noticed, because we have instruments capable of observation. To the object itself, if objects could have perspectives, our solar system is just one gravitational well among countless others, momentarily altering trajectory before releasing it back into the void. Does this relativity of significance diminish meaning? Only if we demand that meaning be universal rather than contextual. Meaning can be real without being cosmic, important without being eternal, valuable without being objective. What matters to us matters, period. No further justification is required. 3I/Atlas came from beyond, passed through briefly, and will depart forever. In the cosmic ledger, this transit registers as barely a footnote, a minor gravitational interaction, a slight deflection of trajectory, nothing that will echo through future eons or reshape galactic evolution. The universe will not miss it when it is gone. No record will remain except in our databases and memories, and even those will fade eventually, lost to the same entropy that awaits all information. Yet this transience does not diminish significance. If anything, it enhances it. We get one chance to study this visitor, one opportunity to learn what we can before it departs. The urgency focuses attention, sharpens analysis, reminds us that time is limited and must be used well. Permanence bride complacency, impermanence demande engagement. What have we learned? That depends on when you ask. Today's answers will seem incomplete from tomorrow's perspective, as they should. Knowledge grows, understanding deepens. New questions emerge from old answers. The process continues as long as we remain curious, as long as we keep looking upward, as long as we find value in understanding our cosmic context. 3I/Atlas matters not because it is unique. It is not, but because it is here, now, accessible to our instruments and our curiosity. It matters because we choose to make it matter, because we invest time and effort and resources into studying it, because we find meaning in the investigation itself regardless of what specific facts we uncover. This is the deeper lesson of interstellar objects, that we are embedded in a vast galaxy full of wandering matter, that boundaries between star systems are permeable, that exchange happens across light years and eons. We are not isolated islands, but participants in a larger community, connected through physics and chemistry to the broader universe from which we emerged and to which we will eventually return. 3. I/Atlas passed through, reminded us of these connections, and will leave. But the reminder lingers. We looked up, saw something from elsewhere, recognized it for what it was, and learned what we could. That simple act of observation, of paying attention, of caring about something beyond immediate concerns, that is what makes us human. That is what gives meaning to our brief existence on this small planet, circling an average star in a galaxy full of wonders. The object will fade from view, but the knowledge remains. The observations persist. The questions continue. And somewhere in the distant future, another interstellar wanderer will pass through, and we will look up again, and the cycle will continue. Each visitor a teacher, each observation a lesson, each discovery a reminder that the universe is vaster and stranger and more connected than our terrestrial existence might suggest.